Hey guys, welcome to another video on parabolas. Now, today we are looking at doing a little bit more sketching of these parabolas, and we're talking about today a specific type of transformation that occurs with parabolas, and this is the idea of a dilation. Now, we've talked about transformations before in geometry with shapes, things like rotations, translations. When it comes to parabolas, the way we work through this is going to be a little bit different. And particularly in this video, we are going to be looking at messing around with some of these values, these types of parabola graphs, and coming to hopefully an intuitive understanding as to the effect of these particular dilations on the different shape of the parabola. Now, what I have down here is a graph of just a regular, simplest form parabola that we looked at in the previous video. This y equals x squared here. So, when we talked about sketching parabolas in the previous video, we looked at constructing this table of values, and in the same way that we did with linear relationships, where we were saying our little output here, y, was just whatever x was squared. And we can see that at this point we have when x is 0, then y is going to be 0 squared, which is 0. Here when x is 1, y is going to be 1 squared, which gives us 1. And up here when x is 2, y is going to be 2 squared, which is 4. And we get this type of parabolic shape here. Now, this particular graph here, the coefficient of x that's implied here is a 1, right? We've talked about this before with algebra. We can always think of any of these pronumerals having this kind of imaginary, if nothing's written here, we're implying an imaginary sort of coefficient of 1. So in this example, our coefficient of a, if you remember our general form of parabolas, the coefficient in front of x squared, this number in front of x squared, is the letter a we give this for quadratics. Now, what we're looking at today is what happens when we start to mess around with this particular coefficient, this pronumeral of a. And we're going to try a couple of examples in this video and look at the effect of changing this. Now, what we are going to do on this graph, we are going to draw on this exact same graph the graph of y equals 2x squared. So, to do this, we are going to do our table of values once again. So, if I draw my little table of values and pop in some values of x, I want to determine the values of y in the same way we did in the last video, in the same way we did for linear relationships, and I want to get a feel for how this new parabola is going to look. So let's start from, let's just go all the way from -2 up to +2. Okay, so when x equals to -2, my value for x is going to be -2 squared. So -2 squared gives me 4, multiplying by 2, that gives me 8 for my y. Putting -1 into here, that gives me 2 times -1 squared, which is going to give me 2. If putting in 0, that's just going to give me 0. Putting in 1, that gives me 2 times 1 squared, gives me 2 again. And +2 gives me 2 times 2 squared, which is the same as 2 times 4, which gives me 8. Now what I'm going to do is I'm going to plot these points on my xy plane here. Now I realize I need to add a couple more of these, so we'll go 7 and 8 up here. Okay, so we want to first graph this point. When x is -2, my y is going to be 8. So that point's going to be kind of all the way up here, actually off my graph. You can see there's already a pretty massive change here. Now when x equals -1, y equals 2, so that point's going to be here. Because I'm lining up, actually let me actually do this again for this point here. I'm just lining up my x coordinate with my subsequent y coordinate, and to plot these points wherever those meet on our grid, that's where our point is going to go. And I have the point 0, 0 again. When x equals 1, y equals 2, and when x equals 2, going all the way up here again, my y equals 8. So hopefully this looks nice when I actually do it, but if I try to connect these dots to form my parabola, I can see what looks like a much steeper parabola. My y equals 2x squared, that the effect of increasing the coefficient from 1 here to 2 made a much more narrower parabola. Now let's take a look at these actual points. I'm going to draw them in. So I have -2, 8. I have -1, 2. I have 1, 2. And I have 2 and 8. So let's actually take a look at what is actually happening with each of these points if we compare. Now my point down here, -2 and 4, the effect of this dilation, we can see that the -2 coordinate is still the same, but what happens to the y coordinate? It has doubled, going from 4 to 8. So it is increased by a factor of 2. The same things happen here. We have -1, 1, -1, 2 up here. My new graph, y equals 2x squared, has been dilated. It has been stretched up in the y direction. So instead of my 1 here, I have a y coordinate of 2. And for 0, 0, that's the coordinate here. That's just going to be my vertex, my pointy end of the parabola. And I see here and here, I've doubled once again, and here and here. So as I track along my x-axis, looking at what happens at the points when x equals -2, -1, 0, 1, 2, I am always multiplying by 2. So that is the effect of this guy over here. That is the effect of our coefficient. When we transform our y equals x squared parabola, we get every single point along here in the y direction doubling, hence making a narrower, more stretched out vertically graph. Now it's important to note here, this point 0, 0 as well, that's also being stretched by a factor of 2. But the only thing is that when we multiply 0 by 2, when we multiply 0 by a factor of 2, we still get 0, right? So that point is going to remain. So even though it doesn't change, we can still think of it as getting stretched by a factor of 2. Now, if you guys would like, have a go at a couple of other ones. Maybe try 3x squared or 4x squared. Try to either write this up in, you can write it up on Desmos, you can have a go there, or you can try graph it freehand and see what the effect is. But we're going to make a point about the observation we made here. So as the coefficient A gets bigger, the graph gets steeper or narrower. I should say the parabola. Parabola gets narrower. It's kind of getting stretched out here. That is what we mean by our dilations. They are transformations to our original parabola in a particular way. Now, when our A got bigger, when we increased it from 1 to 2, it got narrower. All of the points here, the y coordinates, here, 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 increased by a factor of 2. So if we maybe change this to 3, that would increase by a factor of 3. So maybe this would get even more steeper. I should draw this through 0. You can maybe try graph this up on Desmos or something, or draw it on your own, and you will see that as our coefficient A gets bigger, our graph's going to keep getting stretched out. Now, we started at 1, and we always kind of start with a coefficient of 1 for our regular simplest form of parabola, y equals x squared. Now we've looked at a number greater than 1, say 2. Let's look and see what happens for a number that is smaller than 1. So maybe a fractional coefficient this time. So we have once again my regular parabola, y equals x squared, and I want to see the effect of making the coefficient, instead of 2, a number bigger than 1, I'm going to lower this. So all the numbers smaller than 1, we start to go into our fractions, these portions of a whole. Now, to figure this guy out, y equals half x squared, if I want to draw this, I'm going to once again consult my handy table of values. So, drawing all these points in, I want to once again figure out what the effect is of this half in front. And I'm going to try to analyze that across 5 different x coordinates, going from -2 up to, I'm going from -2 to +2. So when x equals -2, subbing that into here, -2 squared gives me 4, and then half times 4 gives me 2. So I'm going to write that here. Now, -1 squared gives me 1, and multiplying that by half gives me half, and 0 squared times half gives me 0 again. 1 squared times a half gives me half, and 2 squared gives me 4, half of that gives me 2. So I want to now graph my second graph, my second parabola, this guy here, on the same xy plane as my original that is already shown. So when x equals to -2, my y equals to +2. So drawing that in here. So I have -2, the point -2, 2. When my x is -1, my y is going to be a half. So about here. Let's write that just down here. So -1 and a half. I still have the point 0, 0. And when my x equals 1, my y equals half. And when my x equals 2, my y equals 2 once again. Alright, now let's try to draw this guy here. So, let's do this in another color so it hopefully pops out a bit. But, ooh, that's shocking. Let's try one more. Okay, it's as best as I could get it. Now, I have this dodgy looking parabola here, but you can hopefully see that by having this number that's less than 1 here, as my coefficient gets smaller, I can see now my parabola looks a little bit wider. So instead of the original form here, we saw we had a really steep thing happening up here. Now we have a wider arching parabola. And we can hopefully, if you've been paying attention to the points here, you may have already picked this up, but let's compare these points again, these respective points. When x equals -2, on my first parabola, y equals 4, and now here y equals 2. Now 2 is half of 4. That's pretty peculiar, but let's see if it happens all the way through. Now we have the y coordinate of 1 here, my y coordinate of 1 when x is -1, and on my dilated parabola, putting this coefficient in front, making it smaller, I get half, and half is a half of 1. It's a half of a whole. Now for 0, 0, half of 0 is just 0, so we get the same thing happening as we did up here. We get that common point, and as we keep going up here, when x equals 1, my y of my original parabola here is going to be 1, and my y of my dilated one matches, it's scaled by a half once again, because half is a half of 1. And the same thing over here. We have 4, we have 2. 2 is half of 4. So we can see this trend kind of emerging. If we kept drawing further out, we would see that each respective point on my new parabola is going to be half of my original. My y coordinate of my new parabola, my dilated parabola with a coefficient a of half, it's always going to be half of the y coordinate of the original. So let's write down this second observation. As a gets smaller, our parabola gets wider. Now, these are the only two ideas I want you to come out of this session with, this lesson. Now, we'll get into all of these crazy transformations in the next few videos, but as far as dilations are concerned, we can see that changing the coefficient of x squared, this a here, this pronumeral a, actually has some pretty significant effects on how my parabola changes. As it gets bigger, so 2 compared to 1, as my coefficient, my pronumeral a gets bigger, my parabola gets narrower. As it gets smaller, my parabola gets wider. That is the effect of changing this guy over here, my pronumeral of a. You can try a few more examples at home if you'd like to really hone this in and see the effect of this, or you can even try to graph it out on Desmos, for example. So I'll write that here for you guys. Just go on desmos.com or whatever it is and try graphing these. Try changing this a. Try making it bigger, increase it to 4, maybe 10, or go down to like 1/10 or 1/4, and look at how this changes. And we'll see that, well, you will hopefully see, if you follow on with this, that it's going to follow the same patterns we talked about here. As a gets bigger, the graph gets narrower. As a gets smaller, my parabola, my graph gets wider. Thank you so much for joining me today, guys, and I'll see you in the next video.